This is my first visit to perimeter, and I just left yesterday, but I'm kind of already impressed by the atmosphere of the institute and the wonderful buildings and the well-organized visitor program and so on. And I'm trying to stay here throughout this week, so I hope to have more opportunities to talk with you. And for today, I'm going to talk about my recent work about crystal meltings and Toric Calabi-Yau Manifolds. And this work is in collaboration with Hiroshi Okuri, which we put on the record last November. So let me try to begin by describing the problem. So the problem is to count the number of degeneracies of BPS states. So the setting is kind of general. So I'm going to consider some string theory for Path Algebra and Calabi-Yau Manifolds. And then I'm going to consider various difference starting various cycles of the Calabi-Yau Manifold. And then so we want to count the number of BPS states of such a setting. And this problem has interesting connection with various topics, and most notably the connection with the counting problem of radical microstates. And also from game theory viewpoint, it's related to Quiver game theories and also, for example, the counting problem for instantons. And it has, since we are counting BPS states, it has interesting application to ADFCT. And recently there is an interesting discussion about over-person phenomenon and so on. And today I'm going to talk a bit about the connection with black holes. And I'm going to use the technical quivers, and if I have time, I'm going to talk about ball crossing and so on. But let me try to begin by describing the connection of this counting problem with topological string theory. And as far as I know, there are two different connections between this topological string theory and the counting problem. The first problem, the first connection is provided by the celebrated OSB conjecture, which states that when the different charges are chosen, such that we have a large black hole, and supergravity approximation is varied, and then we have the relation like a Z black hole. So this is a position function counting the black hole, counting the degeneracy of the BPS states, and this is equivalent to the absolute Paris field of the topological string partition function. So this is the one relation, which is called the OSB conjecture, and another connection between this counting problem and topological string theory is provided by the so-called crystal meltings, as proposed by Okunko preceding in Baffat and also by Quiver in 2003. So what we propose is schematically saying it's a relation like this. So Z black hole is equivalent to Z topological. So what they consider is the case of a single D6 brane with various D0 and D2 branes. And then they computed the degeneracies of BPS states. And this is equivalent to the topological string partition function, which in turn, in the case of C3, is related to the statistical mechanical model of crystal meltings. Which is shown here. And this was made possible by using the techniques of Donaldson-Thomas theory, which is a kind of mathematical theory. So I'd like to point out that these two relations, in general, hold in different regions of varieties. So even if you have a relation, this relation might not hold, and even if you have this relation might not hold, and so on. And so, I'm going to talk about the relation between these in the discussion. But today, I'm going to concentrate on this case, namely about the crystal melting case. So what's new in crystal melting? Well, originally, the crystal melting was proposed for the case of C3, just plus C3. And of course, it's a Toric Calabi-Yau manifold. And so this kind of crystal melting picture is just for C3. But it was subsequently generalized by using the topological vertex formulation as proposed by Marino and Baffat and so on. And the basic idea is to cut the Toric diagram into various pieces. And then we have a tricovalent vertex, which locally looks like a C3. So by using this kind of crystal melting picture as a basic building block, I can compute the topological string partition function for arbitrary Toric Calabi-Yau manifold. So this is the general idea, but that's a beautiful development, but at the same time, the crystal melting picture itself is proposed only for physical C3.
Can I ask a question? Why is it called crystal melting?
Sorry?
Why is it called?
I see. So I should probably explain. So I think this is first of all, it's a kind of melting cone of the crystal. So there are various boxes shown here, and each of box are meant to be represented by a kind of atom in the crystal. And then I'm going to remove each atom from the corner of the crystal. So in this case, there are a bunch of, say, order of 10 of atoms are removed from the crystal. And then I'm going to remove more and more if I go to the thermodynamic limit and so on. And actually, this kind of crystal mating can be seen in a certain setting in experiment, actually. Well, I'm not sure. I mean, this potential function is actually relevant to the physics experiment, but so it does corresponds to including various numbers of d branes. That's actually what I'm going to explain. So the ground state is just a corner of the crystal, and then I'm going to remove atoms, and that corresponds to including more and more d branes. So that's what we propose. So I was saying that I'm considering single D6 brane with various D0 and D2 branes. So in the case of CC, we have only D0 actually, and then if I add D0, various D0 branes, I'm going to remove various atoms. And the number of D0 branes corresponds to the number of boxes removed from the crystal.
Large black hole as well when you have D0.
But in this case, actually, for the case of D0 and D6, I don't think we have a large black hole. But actually, that's a kind of subtle issue. And naively speaking, D0 and D6 doesn't admit VPS states. But in this case setting, actually, we are including the D field. And there is actually an old paper by Edward Mitchell which say that VPS bound state of D0 and D6 can exist if we include D field. So when we are talking about OSB conjecture, we are talking about black holes. So we are not including D field. So naively speaking, yeah, in that case, since D0 and D6 bound state does not exist. But in this case, we are including D field, so D6, D0 bound state exists. So and that kind of bound state are counted here. So and of course, this is not just a story. For example, there is a beautiful story by Takuya, which proposed to generalize this picture to the case of manifold. But as far as I know, there is no general crystal mating picture for the arbitrary case of Toric Calabi-Yau manifold. So, and our work has succeeded in generalizing this crystal mating picture to the case of completely arbitrary Toric Calabi-Yau manifold. And this was made possible by the recent development in non-commutative Donaldson-Thomas theory, which began in the work by Stanford in 2007, and also by multiple boys in Nike. So these people are mathematicians, and this paper is actually quite kind of new, which appeared just last September last year. And these are kind of mathematical theories, but if you look at their papers and try to understand what they are saying, this problem is actually almost equivalent to the counting problem bound state of D-branes, which I was talking about in the previous slide. So by using this newly developed theory, we have succeeded in proposing a new statistical mechanical model of crystal mating for the case of arbitrary Toric Calabi-Yau manifolds. So that's what I'm going to explain. So I'm almost finishing the introduction, but is there any questions so far? Okay, if there is none, I'm going to talk about my plan. And this plan looks very complicated, but basically I have already finished the introduction, and also I'm going to talk about supersymmetric quantum mechanics, but this is the kind of preparation for the story about our new crystal mating model. So this is the most important part, which I like to spend most of the time. And if I still have time, I can talk about the relation between how we came to the result using this mathematical theory. And also, I'd like to discuss the connection with wall crossings, which is a kind of hot topic these days. So let me begin by describing the supersymmetric Quiver quantum mechanics. So why do we have to consider supersymmetric quantum mechanics? So before explaining that, let me try to be a bit more specific about what kind of configurations I'm considering. So I'm going to consider type 2A string theory compactified on Toric Calabi-Yau threefold. And so this is a non-compact Calabi-Yau manifold. And then I'm going to consider a single D6 brane fitting the entire Calabi-Yau manifold. So recall that D6 brane has word volume 6 plus 1. And so this D6 brane fitting the entire Calabi-Yau manifold looks like just like a particle from four-dimensional viewpoint. And also, I'm going to consider various numbers of D0 branes and D2 branes. So these D0 branes looks like a point, and these D2 branes have 2 cycles of the Calabi-Yau manifold. So again, these also look like particles from four-dimensional viewpoint. So the word theory of these branes from four-dimensional viewpoint looks like a quantum mechanics. And actually, it's a Quiver quantum mechanics. And so the question is, what kind of Quiver quantum mechanics we have? And this has quite a long history, dating back first to the work by Douglas Moore in the case of orbifold. And it was subsequently generalized to more complicated Toric Calabi-Yau manifolds. And there are various techniques to do this by using, for example, exceptional corrections, derived categories, and so on. But But the technique I'm going to use today is the so-called brain tiling techniques as proposed by Hanoni and collaborators since 2005. Well, I have written a kind of extensive review about this topic, so if you are interested, you can have a look at it. But let me try to give a kind of overall view summary of what these kind of techniques has to say. So, so the important point is that brain tiling techniques gives first a Quiver diagram and a superpotential starting from arbitrary Toric Calabi-Yau manifold. So Toric Calabi-Yau manifolds are just special class of manifolds in which basically everything is encoded in a complex polytope, which is called the toric diagram. So this is an example of the toric diagram. And then starting from this toric diagram, I can write down by using complicated techniques the Quiver diagrams on two-dimensional torus. And well, these are not just a kind of mnemonics, but they have physical meaning as clarified in a paper by Quiver and collaborators. And also, I have also done some work about this. But the important, so these figures might look complicated, but don't be discouraged right now because these are not really needed. So the important thing, most important thing I should say, is that Quiver diagram is written on the two-dimensional torus. So this is a Quiver diagram where we have gauge groups UN here, UN here, UN and K here, and so on. And then these arrows correspond to bifundamentals. And so these Quiver diagrams specify the matter content of the gauge theory. And then this Quiver diagram is drawn on a two-dimensional torus. So, well, I forgot to say that this green square is meant to be the fundamental region of the torus. So we have an edge here on the right and an edge on the left. So, and these edges are identified, for example. And of course, the edge on the top and the edge on the bottom are identified and so on. And if you look at this figure, there are seemingly 4 different vertices. But since this is a torus, this vertex and this vertex are identified. So we only have 3 vertices. And if you count carefully, there are 7 number of arrows. So this is, if you forget the fact that this diagram is written on the torus, it's just a Quiver diagram shown like here. So what's the merit of writing the Quiver diagram on two-dimensional torus? Well, the merit is that it encodes simultaneously the information of the Quiver diagram and the superpotential. So let me try to explain in this example. So this is an example. So this is actually the same example, completely the same example as this one, although it looks slightly different. And I have numbered the arrows. Like, for example, there is an arrow going from vertex 3 to vertex 1, which I have numbered as x31, and so on. And then each of the arrows is represented as xij. And then, for example, there is a triangle here. And if you go along the orientation of arrows, you have a product like x31, x13, x33. And this corresponds to a certain term. So this term, x33, x31, x13 in the superpotential. And so on. And if you look carefully, there are actually 4 different phases. And each of the phases contributes to a certain term in the superpotential. So this is the general rule. But as I emphasized, the important thing is that in this kind of brain tiling techniques, the Quiver diagram which specifies the matter content is written on the two-dimensional torus. And from which information, we can read off the Quiver and the superpotential. So recall that I'm considering supersymmetric quantum mechanics, which is a dimensional reduction of 4-dimensional n=1 supersymmetric gauge theory. And in order to specify n=1 supersymmetric gauge theory, we have to specify first the matter content, what kind of gauge groups we have, what kind of matter fields we have. And also I have to specify the superpotential. And all these information are encoded in the Quiver diagram written on the torus. So this is a kind of classical summary of what, what brain tiling techniques tells us. And based on these techniques, I'm going to describe the new crystal mating model. And the important point is that BPS state, which we want to count, is in 1-to-1 correspondence with a configuration of a molten crystal. So I'd like to show you an example of crystal, which looks very complicated, but don't be afraid because I'm going to take time to explain. So there are 2 figures, and the figure on the left is a Quiver diagram written on 2-dimensional torus. And I have lifted the diagram to its universal cover. So, well, previously, there was a figure like this. So this is a Quiver diagram on the torus. So each of these squares is a fundamental region of the torus, and so on. But I have lifted this graph to a universal cover. So it's a kind of periodic graph written on the 3-dimensional plane. So we have various vertices and various arrows and so on. And I have previously explained that we can obtain this graph starting from the toric diagram, namely from the geometry. And then what we do is to write a configuration of the atoms like this. So this corresponds to a kind of ground state. And and because that I said I'm going to consider a single D6 plane with various number of D0 and D2 planes. So as a very special case, I can consider the situation where we include only a single D6 plane without any D0 and D2 planes. And that kind of EPS state corresponds to this unmolten crystal. And so let me take some time to explain how I drew. So I came to this result. So first of all, there are various vertices on the figure on the left. And each of the atoms here, on the figure on the right, corresponds to a vertex on the left. So for example, there is a blue vertex here, and there is a corresponding blue vertex here, and you have correspondingly a white atom here. And also say there is a red atom here, red vertex here, and correspondingly there is some atom here, and so on. And the important point here is that atom has different colors. So I fear that some people sitting behind might not be able to see well. So I have magnified this figure around this blue point. So the figure looks like this. And well, recall that each of the vertex here is originally one of the vertices of a Quiver diagram. So originally I have a Quiver diagram like this one, and in this case we have 3 vertices. So each of the vertex has either number 1, 2, or 3. So correspondingly, each of the vertex here has also numbers. And according to that number, I'm going to color the atoms, in this case like black, gray, and white. But the color, there is no definite meaning to the color. So if you like, you can color by green, yellow, red, or something. But in this case, I have used this color. And so if I repeat, I'm tracing the atom for each vertex of the crystal, and I'm going to color the atom according to the position of the vertex in the original Quiver diagram. Well, so this looks complicated, but there exists a kind of another way to say what this crystal is meant to represent. And another way of saying that is that each atom in the crystal corresponds to an equivalence class of paths starting at the reference point. So I have chosen a certain point, which I call the reference point. This is the blue point here. And then I have specified the reference point, and then I'm going to consider the set of all possible paths starting from this vertex. So there are obviously various paths. Like, for example, you can go here. Also, you can go here, 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 and go back, and so on. So there are various paths. And recall that each arrow corresponds to a bifundamental field. So a field in the gauge theory. And I have computed the superpotential using brain tiling techniques. So if you differentiate that with respect to a certain field, we have the F-term constraints, which means that certain paths should be equivalent to another path, and so on. And I'm going to identify all the paths which are equivalent under F-term constraints. So let me try to give you an example. So for example, there I have drawn a path here, like shown here. And then this is identified with the set of paths shown on the right. Well, this is because you have a term in the superpotential corresponding to this space, and also another term in the superpotential corresponds to this. And if you differentiate the superpotential with respect to this bifundamental field, you have a relation like that this path is equivalent to this path, and so on. Well, but the important point is just I'm going to consider the set of all possible paths starting from a particular vertex on the Quiver diagram leading on the two-dimensional torus. And then there exists a kind of theorem which says that each set of paths, well, I should like instead of arrow, I should call it the path. Each path starting from this I0, this difference path, from any other point I, is equivalent under F-term constraints to Vi times omega j, where Vi is the shortest path starting from this vertex to the I destination, and omega is the set of paths. It's just a path circling around the face. So let me try to give you an example. So this is the reference point, and I have chosen another point I. And this green arrow is just an example of a path starting from I0 and ending at I. And in this example, it's almost obvious that the shortest path starting from this to I0 to I, is this represented by this green arrow. So according to the theorem, we should be able to represent this green path as a form like this. And you can actually do this because, as I have explained, this operator, or I should say the operator corresponding to this set of paths, is equivalent to the set of paths shown here. And this just corresponds to the first going along this BI, the shortest path, times going around the circle and so on. So each of the paths can be written as the BI times omega j, which means that every path or every atom is specified by two numbers, two data. First, the position of the atom, position of the endpoint, and also this number j. So corresponding to that, I'm going to place the atom here. So I've said previously that all of the paths, suppose that I have a path starting from I0 and going in a very, very complicated way, and suppose that it ends at a certain point. Let me call it I. And then from the previous theorem, we learned that it should be equivalent to this BI times omega j. And I'm going to represent this path as an atom in the position I with the depth j. So probably I forgot to say that this is meant to be a semi-infinite configuration of crystal. So for example, I have here an atom, and I have another atom below it, another atom further below it, and so on. And we have so infinite number of atoms below it. And also this kind of corresponds to a kind of reach of the crystal. So it's like a pyramid, almost like a pyramid. So we have this is the top of the pyramid, and this is the reach of the pyramid, and we have infinite number of atoms below all these things. So well, probably I have explained a bit too detail, but the important point is that given a toric diagram, namely the geometry, there exists a systematic method to construct the crystal model like this. And I said that this corresponds to a single D6 brane without any D0 and D2 branes. So the natural question is, what happens if I'm going to include D0 and D2 branes? And well, that corresponds to a configuration of a molten crystal. So this, again, still looks complicated, but the important point is that I have removed all these atoms, say 10 or maybe 12 or something, of atoms from the original unmolten crystal. And each of the atoms, whether either colored white, gray, or black, carries certain combination of D0 and D2 brane charges. So I think this is a generalization of what Kumran did in the case of C3. So there was already a question about that. So in the case of C3, we are considering just D6 brane and various D0 branes. And then including various D0 branes correspond to removing various atoms from the crystal. And it's almost similar to the case here. So I'm going to consider various this single D6 brane with various D0 and D2 branes. And well, in this case, I can include the D2 brane as well. So we have various possible charges of D branes. And then, well, if I'm going to consider a bound state with various charges, that corresponds to removing the atoms. But the difference for the case of C3 is that we are considering a situation where each of the atom has colors. And that corresponds to the fact that we can consider various D0 and D2 brane charges in the corresponding Toric Calabi-Yau manifold. So any questions so far? Okay, so this is the kind of statistical mechanical model. And I'm going to, and the important point here is that every BPS state contributes into the index, actually. So actually, I'm considering Witt index of the supersymmetric Quiver quantum mechanics. And so BPS states are constructed out of atoms shown here. So in this case, there are 3 atoms, 3 corresponding to the number of vertices of the Quiver diagram. And each of the D branes carry linear combination of D brane charges. And well, this is the important point is that each of the atoms carries linear combination of D brane charges, not the D brane charges themselves. And this is a kind of reminiscent of the Cloak models as opposed to the Sakata models. So in the old days of elementary particle physics, Sakata proposed that, for example, neutrons and protons and lambda particles, there should be the basic fundamental constituent of nature. So that's what he proposed. But actually, that's not the case. And it turns out that their linear combinations, like quarks, are really the fundamental constituents of nature. And this is, in a sense, similar, in the sense that so we are considering the D6 experiment with various D0 and D2 branes. So naively speaking, you might guess that D0 branes and D2 branes themselves might be the basic constituents of BPS states. But that's not the case in this, actually. And what we found is that their linear combinations, the atoms shown here, are the basic constituents. And this is a kind of reminiscent, although slightly different, but kind of reminiscent of the, for example, bubbling APS geometry as proposed by LLM and also by fast flow conjecture and so on. And so, well, this might have some interesting applications, although we are not currently sure. And, well, I was telling you that I'm going to remove atoms from the crystal. But, of course, sorry? Can PQ5 brane base. So that depends on what you mean by in the context. But for example, there exists a relation between this crystal model and the PQ5 brane base, for example. So I was saying that this is like a pyramid with the reaches spreading in these directions. But actually, there is a kind of correspondence between the direction of these lines, the reaches of the crystal, and the PQF. Well, but that's kind of actually what we conjectured in a paper. So there exists a systematic method to write the figure like this, and we conjectured that the shape of the reaches should coincide with that of the PQF. But
corresponds to the PQ5 right? So what's the BPS state that corresponds to the PQ5 in the context of PQ5 right?
Well,
is it possible to find, for example, connecting some kind of piece of the PQ5 ring to the diagram?
well, I see. Actually, I think that one of the answers is that if you take the sum dynamic limit, you are going to reproduce the PQF. Actually, I was planning to talk about it in the discussions, but let me try to take some time to explain that, since there was a question. So I think that corresponds to some of the sum dynamic limit of the system. So probably, I hope that this might answer some of your questions. So in the case of C3, the PQF is something like a trivalent matrix. And in that case, we have a melting point on the crystal, and I'm going to remove various number of atoms. And then if I'm going to take some dynamic limit, namely, if I'm going to remove various infinite number of atoms, and then we have a shape like this. And then this shape is kind of called the limit shape. And if you take the limit where the thickness of this figure shrinks to 0, and then you are going to reproduce the PQ5 rate shown here. So actually, complete similar story goes for the case of arbitrary manifold. So in this case, well, I should probably go this way, back to the original slide. So let me see. So this is the original slide. And so that's the same thing happens in this case as well. So this is just the infinite combination of crystals, and I want to remove various numbers of atoms. And then if you take the limit, some dynamic limit, the figure like that. So original configuration looks like almost like a pyramid. So we have a face here, another face here, another face here, another face here. And I'm going to remove various atoms from here, and so on. And if I'm going to remove infinite number of atoms, and then we have a figure like this one. So atoms are removed here, and the corner has melted away. And in each of these regions, the atoms are not removed at all. But in these regions, atoms are removed. And then if you take a limit, we have a kind of PQ there, shown here. Actually, we are kind of writing a paper about these some dynamic limits, which will appear quite soon, I think. And so probably, yeah, I think that answers some of your questions. So let me see what else to do. Any other questions? Okay, so let me see. I have 30 minutes or so, but let me see. So let me try to explain a bit more about this. So I said that I'm going to remove atoms from the crystal metric configuration, but there exists a certain condition. So in the case of C3, we have a melting point of the crystal, and I'm going to remove atoms, for example, from here. This is here, and if I'm going to remove one more, it looks like this, and so on. So I'm going to remove various atoms from the crystal, but you cannot suddenly take, for example, an atom from here. This kind of things is forbidden. So I have to so I have to impose certain conditions for how to remove the atoms. And that kind of rule is deformed as a melting rule, shown here. So I have the set of arrows, and then suppose that I'm going to write the atom in the complement of the this omega. Well, I should say. So this is omega c. So I'm going to denote the set of atoms removed from the crystal as omega c, and the set of atoms unremoved from the atom as omega. And then I'm going to impose the condition that if this A alpha, so there is an atom here, and there is an atom here, and let us write the atom at the end point of the arrow as A alpha, for example. And then I'm going to impose the condition that if this A alpha is included in this omega c, I mean the set of atoms removed from the crystal, then the alpha should also be included in omega c. So let me try to see in this example. Well, so in this example, for example, there is alpha here, and there is an atom A here, and then the atom at the end point is giving A alpha. And this condition says that if this A alpha is included in omega c, and then alpha should also be included in omega c, and so on. So this is the kind of rule for how to remove the crystal. And one last thing I'd like to say is that I was talking using the language of crystals, but this is equivalently formulated as a diamond model. So instead of using this, we have a configuration of the so-called perfect model. So let me try to explain. So in this case, the vertices, there is a graph with the graph and 5 vertices. And this kind of graph is a very special graph for the bipartite graph, because each of the vertices carries either a graph of 5, and graph vertices connected only to 5 vertices, and 5 vertices connected only to 5 vertices, graph vertices, so on. And then a perfect matching corresponds to a subset of edges, such that each vertex is chosen exactly once. So it's like a coupling problem of men and women. So we have the set of graph vertices and one set of white vertices, and I'd like to make a pair choosing each one from the set of graph vertices and one from the set of 5 vertices, and so on. And so each of these configurations can be identified with the configuration of a perfect matching in the diamond. So some people might like to use this, or some people might like to use this, and well, so that depends on your preference and your taste. So probably I was going a bit too technical, but the basic point is that starting from the toric diamond, I can write down the crystal, and then each BPS state, every BPS state contributing to the index can be written down by just removing atoms from this melting crystal configuration.
You are going to prove this statement.
Yeah, actually. I'm not going to go into too much detail, but I'm going to prove this statement. That's what I'm going to do in this section. So I'm going to kind of prove, well, I'm not going into too much detail, but kind of give you a basic outline of how we came to the result using mathematical theory called the non-commutative Donaldson-Thomas theory. And so mathematically, so I was talking originally about the counting problem of BPS states of various Liebens, having homologic cycles, and this is reformulated as a non-commutative Donaldson-Thomas theory. And if you look at the literature of non-commutative Donaldson-Thomas theory, there is like a Path Algebra, its module, and compactation of moduli space, stability, and so on. So there seems to be many unfamiliar terminologies, but if you look carefully, the thing is not so complicated, so let me try to explain. By first introducing a new notion called the Path Algebra. And so I'm going to consider a ring of all possible paths operators, namely operators modeled out by external constraints. So you call that each of the paths corresponds to bifundamental fields. Each is an operator in the gauge field. So I'm going to consider the set of all possible products. So for example, this is an example of the Quiver corresponding to the manifold, and in this example we have A's and B's. So the possible operator corresponds in this case to, for example, AB, AB, BA, BA, and so on. Well, it can be 1 or 2, either 1 or 2. So there are various possibilities. And they are not necessarily gauge invariant. So of course, most of them are gauge variable. And I'm going to consider a set of all such operators plotted out by F-time relations. And this is a kind of non-commutative algebra. So let me try to explain why this is non-commutative. So I have an arrow here, for example, and I have another arrow here. And then, so I said that this is a ring, so I have to define a multiplication. And I'm going to define a multiplication by just concatenating these three paths. So this is n to the a times b. But of course, this is not always possible. Suppose that the endpoint of this, for example, arrow A, does not coincide with the starting point of another arrow B. And in this case, there is no way to define a concatenation. So in this case, a times b is non-zero, but in this case, I define the concatenation as 0. So in this case, for example, b times a is 0, because the endpoint of this b is different from the start point of this arrow A. So this is actually kind of non-commutative algebra, which is the origin of the name non-commutative Donaldson-Thomas theory. Well, this looks like a terrible formalism, but what the mathematics literature says is that computational Witten index of the supersymmetric quantum mechanics is equivalent to the counting of set of stable A modules fixed by two-dimensional torus. So let me try to explain step by step. So first, recall that this A is the set of all possible paths on the Quiver algebra modeled out by F-time relation. So it's some algebra. And then I'm going to consider its module. And modules are basically representations. So this is just a kind of very formal thing with various, I'm just considering various arrows and the concatenation and so on. They're very formal. But in physics situation, we have to consider its representations there. So that corresponds to considering what is called A modules in the mathematics literature. And I'm going to compute the Witten index and count the BPS space. Thus, I'm interested in the moduli space of the supersymmetric Quiver quantum mechanics. And the moduli space is specified by two data. The first by the F-term constraints and the D-term constraints, of course. And then have to divide by the gauge group. That's the way to compute the moduli space. And I want to compute the Euler character of that moduli space. So we have to take F-term constraints and D-term constraints into account. And here, I've already taken the F-term constraint into account because I have modeled out the path algebra by the F-term relations. And then I have to consider D-term constraints. And of course, one of the ways is to just write down the F-term constraints and D-term constraints and divide by the gauge group. But there exists another way to do that, namely to just solve the F-term constraints and then divide by the complexified gauge group. That's one of the ways to compute the moduli space. And there exists a certain condition that orbit of the complexified gauge group should contain the solution to the D-term equations. And that condition amounts to the so-called stability condition. And there exists a certain parameter theta here. And the physical meaning of this parameter theta is that it's related to the Fi parameter of the case. So recall that in order to write down F-term constraints, I have to introduce Fi parameters in general. So I have to introduce certain parameters, and depending on the value of the parameter, the moduli space changes in general. And this parameter theta introduced in some mathematics literature basically corresponds to the Fi parameter in the case theory. So I have taken care of F-term and D-term constraints, and thus we can study the moduli space. But then the moduli space is finite dimensional. But then we have a localization theorem. So recall that I'm considering toric geometry, which we have an action of the torus on the geometry. And correspondingly, we have an action of torus on the moduli space. And then we can use the localization theorem, which says that in order to compute the Euler character of the moduli space, all we have to do is to consider all the possible fixed points of the moduli space fixed by this torus action, and then sum up everything, sum up the contribution coming from each fixed point. So this is a kind of localization theorem. And by using this localization theorem, the counting problem BPS space is equivalent to the counting problem of theta stable A modules fixed by two-dimensional torus. Well, so this might still look like a terrible mathematics notation, but it's actually, so what I should talk about is that the relation between this mathematics problem and the configuration of molten crystal. So probably I should try to, well, I have used. So, oh dear, I can use another blackboard here. So the original problem I was talking about is counting of BPS states. And this is equivalent to counting of modules. But there exists a certain condition like a stability that, but I'm not going to write it here. And then this is equivalent to configuration of molten crystal. So I think I have tried to explain what this equality. So I should explain this equality. So the problem is to construct a module starting from a configuration of molten crystal. So let me try to do that. Well, I should use here, but so let me try to go back to the example of the previous slide. So let me see. So for example, there is an example here, but this looks very complicated. So let me try to do in a slightly smaller example. For example, this example, I think. Let me see. For example, in this example. So we have white atoms here. There is a blue vertex here, and there is this black atoms here, and also gray atom here, and so on. So this is a particular configuration of molten crystal, and I'd like to define a certain module of the path algebra, and I'm going to do this in a simple rule. So for each atom, the first of the rule is that for each atom, I'm going to put a one-dimensional vector space. So, and let me denote its basis as EI. So in this case, for example, since I'm reviewing 5 different atoms, I'm going to consider 5-dimensional representation. So recall that module is basically like a representation, and I'm going to consider finite dimensional representation. And in this case, I'm going to consider 5-dimensional representation. And then there are a set of atoms, a set of arrows going in these directions. So in order to make a representation of the path algebra, I have to assign a linear transformation. So suppose that there exists an arrow like here, x, y, z. I should write larger so that people can see. ZWU, for example. And then the action of x is defined by sending E1 to E2, and all others 0. This is chosen because the arrow x just starts from x, E1, and E2. But all the others are not included in this configuration. And for example, y is defined by just sending E1 to E4, and all the others 0, and so on. And you can define, for example, z is when sending E2 to E3, and so on. And then each of these 5 fundamental fields can be written as a linear transformation on this vector space. So I'm considering the vector space, and each of the arrow corresponds to a linear transformation. So they can be written as a matrix. And by using this method, I can construct the representation of the path algebra. And of course, the most difficult part is that to show that all possible modules can be constructed using this crystal melting configuration. And that is what mathematicians did, mathematicians proved. Well, so anyway, I wanted to try to explain why this counting problem can be reformulated as configuration of molten crystal. And if you look at our paper, there exists another way to explain that. So if you're interested, you might prefer that explanation as well. So that's what basic idea of what we came to the proof, how we came to the proof. Sorry? What? Where?
So you are going to explain the connection between 3 objects.
I see. Actually, that's what I'm going to explain right now. So I just explained the counting relation. So far, I will just explain the relation between counting problem and the crystal. And I'm not saying anything about topological string theory. So I should explain that. So that's what I'm going to do from right now, actually. And the connection is kind of subtle, as I'm going to see. So what Kuhlmann incorporated this originally is that topological string theory is related to the so-called commutative Donaldson-Thomas theory, which I write here. And then what I was talking here today is the counting problem of crystal theory. And this is in one-to-one correspondence with the completion counting problem. But I have put the prime here in this formula. Well, the reason is that this is counting problem commutative Donaldson-Thomas theory, whereas this is a counting problem in non-commutative Donaldson-Thomas theory. And the difference between these is that the left-hand side is evaluated at different points at the Quiver modulus infinity. So recall that I'm considering a counting problem of the various BPS states. But actually, that depends on the value of Quiver modulus at infinity. And but if you, in generic situation, if we change the value of Quiver moduli, infinitesimally, the BPS state does not change at all. But there are certain four-dimensional walls in the Quiver moduli space, which is often called walls of marginal stability. And if you cross the walls of marginal stability, the BPS state actually changes. So when I write the partition function like a Z graph 4, there actually exists a dependence on the value of Quiver moduli at infinity. So these are, in general, different quantities. And in order to relate this to this, I have to cross many infinite number of walls. So I have to take the wall crossing phenomena into account. And there exists a beautiful formula due to conservation in Solzerman, which says that how the BPS state jumps along whenever I cross the walls of marginal stability. So the correct statement between topological string theory and crystal melting is that crystal melting is equivalent to topological string theory module wall crosses. This is, I think, a kind of new feature of our crystal melting. Because that in the case of C3, actually, there is no wall crossing phenomenon. So there is nothing wrong about what Muran, Lesifican, and Okunku did. And well, in that case, we have a equality. Crystal melting is itself equivalent to the topological string theory. But in general, since this is a counter problem in different jump of the moduli space, there exists a certain factor coming here. So these are not equivalent, but equivalent only if we take the wall crossing phenomenon into account. Does that answer your question? Or?
So in the case of non-commutative field theory, there is a parameter, non-commutativity parameter.
I see. So your question is how the non-commutative parameter appears in this construction. I'm not sure. I think that's an
Is there a continuous parameter?
Actually, there is no continuous parameter in this construction. There exists a certain stability parameter, but that's different from non-commutativity parameter because, as I said, that just corresponds to F5 parameters. And so I think that's an interesting question. And one of the ways to explain that is that in this situation, if I believe in what Greg and Frederick, Dennett, and so on other people are saying, we are considering a situation with infinite field. So the original story about non-commutative field theory and so on in the Cyber paper is that if you include a B field, you have a non-commutative theory. And well, naively speaking, it seems that B field seems to be rather large in this setting. So probably that might explain the meaning of that.
So the usual commutative Donaldson theory corresponds to B field equals to 0.
Well,
commutativity theory, non-commutative Donaldson-Thomas theory corresponds to B equals infinity.
well, actually, the story is not that simple, I guess, because well, some people say that Donaldson-Thomas theory corresponds to the B field in infinity, actually. So that's a kind of complicated situation. Actually, frankly speaking, I don't know the answer. So at least there is a statement in the Jeffrey Murat paper, for example, which says that non-commutativity, non-commutative Donaldson-Thomas theory should be related to inclusion of B field. But that's just a proposal, proposal. So I'm not sure. Whether there is actually a relation between this non-commutativity and the inclusion of B field. And I think that's an interesting problem. But only one possibility, one possible explanation I can think of that B field is infinitely large. So there is no commutativity parameter and so on. But I don't know. That explanation might be wrong, or maybe correct. So, and well, mathematically speaking, the meaning of non-commutative is just to consider non-commutative algebra. So I'm going to consider algebra which is a non-commutative algebra. That's the meaning of non-commutative. And in that construction, there is no, deformation parameter. So I was explaining this, so let me try to give you an example of each of these cases. So in the case of conical, the Donaldson-Thomas theory, which corresponds to the topological string partition function, is written in this one. We have the so-called maximum function, and we have another function here. And the non-commutative Donaldson-Thomas theory looks almost similar, but coming with a different factor shown here. And there exists, so this is basically corresponds to well, I should say that this corresponds to the parameter space or the parameter sequence, which I introduced previously. So I was talking about the counting problem of the stable modules, and in this case, there are two sequences, theta 1 and theta 2. So we have theta 1 going in this direction, theta 2 in another axis. And then we have a set of walls of marginal stability. And then the Donaldson-Thomas theory corresponds to this actually a very small region here. And the non-commutative Donaldson-Thomas theory corresponds to the counting problem in this value of the variable, or more precisely speaking, the value of the stability parameter. And if you want to go from here, Donaldson-Thomas, commutative Donaldson-Thomas theory to non-commutative Donaldson-Thomas theory, you have to actually cross infinite number of walls. And that gives you this infinite product. So each time, so this k runs from 1 to infinity. So it's an infinite product. And each time if you cross this wall, you get extra factor like 1 minus q inverse q to the power k times k. So you get one of these each factors each time you cross this wall. And since you're crossing infinite number of walls, you have this infinite product. This is the difference between commutative Donaldson-Thomas theory and non-commutative Donaldson-Thomas theory. And there exists a formula which says that if you know the partition function in a particular region, say here, and then you can compute the partition function in another region, at least in principle, and that's the so-called wall crossing formula. And there is a certain discussion about this recently. So I think it's almost time. So let me try to wrap up. So I was considering a new crystal melting model which captures the bound state of D0 and D2 and a single D6 springs with various various chromatic cycles of the Calabi-Yau manifold. I should say Toric Calabi-Yau manifold. And then the important point is that our crystal model applies to the case of arbitrary Toric Calabi-Yau manifold. And what we found is that each BPS bound state is in one-to-one correspondence with the configuration of molten crystal. And this crystal melting model has some new features, like for example, well, I'm not sure how essential this is, but we have used the Path Algebra which is certainly non-commutative, so we have some non-commutativity emerging. And also, for example, atoms have different colors, which is a kind of new feature, because in the case of C3, we have only a single type of atom, whereas in this case, we have different types of atoms making up the chemical bonds and connections and making crystals and so on. And I think this is a kind of new feature. And one of the things I was explaining here is that in order to properly understand the relation between this crystal melting feature, at least other crystal melting model, and the topological string theory, we have to think carefully about the wall crossing phenomenon. And that's also another a new feature of our model. And there are various things I think which should be done. And one of the things I'm currently doing, which might appear quite soon, is the thermodynamic limit of this statistical mechanical model. So in a sense, we are doing a kind of statistical mechanics. I'm going to consider the ground state, and I'm going to consider excited state, each excited state, and so on. And then the natural question is what happens if I take the thermodynamic limit. And in this case, the thermodynamic limit corresponds to removing infinitely many atoms from the crystal. And well, I was explaining previously that in the case of, for example, if, in this example, I was explaining, if you take the thermodynamic limit, we should have a figure like this. And this kind of figure, in this case, this line corresponds to these lines, and these lines are sometimes called limit shapes in the context of diamond models and crystal melting fixture. And so the interesting thing is that this shape of the crystal exactly coincides with a certain Lagrangian in the Miller V model. So the important thing is that if you take the thermodynamic limit, the classical geometry naturally emerges. So this coincides with geometry of the Miller V model Calabi-Yau manifold. So I'm considering type 2 string theory on a Calabi-Yau manifold, and then the geometry shown here corresponds to the Miller Calabi-Yau manifold. And so, in that sense, the classical geometry is kind of reproduced from the crystal. And since the diamond model, as I was explaining, the crystal melting model is equivalent to the diamond model, and the diamond model is actually almost exactly solvable. So one of the ways the diamond model was started in the 1960s is that it was used to solve the item model, for example. And it's, in a sense, exactly sort of model, so we can compute correlation functions and so on. And so probably we might be able to think about the meaning of fluctuation and so on, and that might have interesting implications for black hole physics, for example. And well, there are other various things I can think of. Well, for example, I was originally talking about, so I began this talk with by saying that there are two different connections between this counting problem and topological string theory. One is the OSB conjecture, one is the crystal-based picture. And well, of course, as I pointed out, these two relations, one the OSB and the crystal medians, are in general holding different regions of validity, but in some cases, these two relations might hold. And by combining these relations, right, naively speaking, we have a relation like Z topological is Z topological squared. So of course, you might think that is nonsense, but of course, the argument inside the Z topological are different. And of course, as I was telling you, these Z black hole and Z black hole here on the left-hand side and on the right-hand side are evaluated at different points of the Taylor moduluses. So if you want to go from here to there, you have to cross infinite number of walls probably. And also, you have to make sure that the different charges are chosen so that we have a large black hole and the supergravity black hole explanation about it, and we can use the OSB conjecture and so on. So there are various things I should consider, but I think it is possible that we have a relation like Z topological and Z topological squared. And I guess that something like, if this kind of relation holds, I guess that something like S-duality might be involved here. Because, for example, the chemical potential appears in this OSB conjecture as a kind of inverse as an argument, but in this case, we have the chemical potential itself appears here. So something like a S-duality might be involved. And well, if I have a relation like this, this might determine the topological string partition function completely. We're just solving this equation. So I think that might be an interesting story. And another story is to consider, so I was originally talking about non-commutative Donaldson-Thomas theory, but for the arbitrary Toric Calabi-Yau manifold. But in the usual commutative Donaldson-Thomas theory, there exists a topological vertex formalism, which makes it possible to compute a topological string partition function for an arbitrary Toric Calabi-Yau manifold. And these are related by wall crossing. So by going through wall crossings, we should be able to find something, a kind of counterpart of topological vertex for non-commutative Donaldson-Thomas theory as well. And I think this is an interesting possible direction. And well, another possible direction is to include these D4 branch charges. And so originally I was talking about D0, D2, and D6 branch. But from the viewpoint of non-commutative Donaldson-Thomas theory, there exists no obstacle, completely no obstacle to including D4 branch. And but the important point is that there exists no counterpart in the commutative Donaldson-Thomas theory for some reason. Well, there exists a sort of counterpart, but that's not widely discussed. And also the structure of the walls. So I was explaining the case of manifold. There exists an infinite number of walls between commutative and non-commutative Donaldson-Thomas theory. And that kind of structure is completely unexplored when we include the 4-branch charges. So that might be a kind of interesting way to generalize the Donaldson-Thomas theory. So these are the possible directions I can think of. And let me try to finish by talking something about a bit more philosophical. So one of the things we found is that BPS state can be constructed out of atoms. And each of the atoms are, in a sense, like atoms of space-time, or like in a sense, like quarks. And as I was telling you, if you take the sum dynamic limit, I'm going to reproduce the classical geometry of the Calabi-Yau manifold. This is when we are going to send the string coupling constant to 0. But if you keep the string coupling constant to finite, in a sense, the geometry of the Calabi-Yau manifold is discretized. And the quanta of the spacetime looks like this atom shown here. So I think this might give a kind of possible clue to how we perceive spacetime in quantum gravity. So, so thank you very much for your attention, and this is the end of my talk.
Questions?
One question. This melting crystal originally came in order just to count BPS state.
Right.
A nice way of organizing them. But in the end, when you talked about the thermodynamic limit, as far as I understood, there is a sense in which the effective dynamics of fluctuation is local on the crystal.
Effective dynamics is what? Sorry?
That we have some effective local dynamic on the crystal that mimic the geometry.
Local dynamics? Oh, sorry, I still don't get it.
Local dynamics
Local dynamics is encoded by crystal or
on the crystal.
local dynamics on the crystal. So if I want to take the sum dynamics itself, I mean the local fluctuation. I mean that depends on the meaning of the local fluctuation, but
you said that it's the same as the geometry.
Right. I mean, if I take some of the serious, well, let me see. The meaning, what I meant by saying that the geometry appears by taking the sum dynamic limit is that limit shape which appears after taking the sum dynamic limit coincides with the geometry of the target. Right. That's what I meant. But of course, even if you take the sum dynamic limit, there exists a kind of some dynamic model, and then there exists a non-trivial correlation function and so on, for example.
Yeah.
So I'm not sure what's the meaning of that in the context of, for example, quantum BPS state, but that might have some interesting implications. That's what I'm trying to say. Sorry, does that answer the question, or?
I haven't asked the question yet. There is, for the geometry, there is a limit in which the effective dynamic is local on the geometry.
Effective dynamics is local on the geometry.
In a certain limit, in a classical limit.
He hasn't asked the question yet.
Oh, okay. Sorry. Yeah.
And this geometry seems to arise on this crystal. I'm trying to understand from the crystal point of view why an effective local dynamics on the crystal comes about. Because originally it just came about as a way of organizing if you want to count.
I see. So probably, let me see if I try to understand your question. So your question is, so I was originally considering counting problem of Calabi-Yau manifold and so on. And so it's a kind of, in a sense, it's a kind of global problem because I'm not paying attention to any particular region of the module, like Calabi-Yau geometry, for example. I'm just considering, like, say, D-branes in certain regions, and I'm not focusing on a particular region of the Calabi-Yau modular space. But
now add a little temperature when there is some fluctuation.
Right. So how should I answer?
Okay. So there is a proposal of effective field theory that describes the melting of the crystal. It's called Keller gravity.
Right.
So there is a proposal of effective low energy field theory that describes
and it's local on the crystal.
Yeah.
Right.
What is the principle?
What is the principle?
Why is it local on in this specific representation of the counting of BPS? What is the meaning of two BPS states that are close to each other?
For example, if there exists a certain configuration, and if I remove the atoms, and you have a single atom, for example, and then you have another configuration, and they look similar. So, are you asking for the relation between these two BPS states, for example, or?
I'm just trying to understand how locality comes about in this specific parameterization of the BPS state.
I see. So. I see. So your question is, the geometry itself is of course continuous, but somehow I was claiming that is discretized when I include keep the string coupling constant defined. So the question is how the continuous is broken in that picture.
Okay.
Well, yeah, I don't know how to answer. Yeah, of course, if you're asking me about some deep questions about quantum gravity, I have no idea, but So yeah, one of the answers I can think of is that one of the relations is that kind of localization theory. I was originally counting the modular space of BPS, supersymmetric quantum mechanics, and that itself has dimensions, of course. So it's a continuous modular space. But then I'm using the localization theory to reduce the bounding problem of modular space to a point. Or another answer might be, as Taku was saying, that is from the viewpoint of Keller gravity. And so I was talking about including various Lagrangian two branes. And in the interpolation equivalent class of concurrent buffer, that corresponds to blowing up the geometry, and so changing the geometry. And so there exists a kind of proposal for the Toric gravity, and I think that the hope is that the capture is something called the quantum forms in quantum gravity. So we have the classically we have the single very smooth geometry. So the basic picture is, so I have lost the source where I found the choice.
There's a box. There's a box in front of the screen.
In front of the screen. Oh, I see. So well, I cannot use it. So probably. The quantum form picture as proposed by Quiver and other people is that the thermodynamic limit, for example, in the case of CC looks like this. So it's like a very, classical, very smooth geometry. And then, so this is the case of string coupling constant almost zero. It's a thermodynamic limit. And what I was talking about is that this corresponds to removing, for example, atoms, for example, a certain number of atoms, for example. Well, this is the kind of table here. But anyway, so I'm going to remove a various number of atoms from this melting point of the crystal. So it's a kind of discrete situation. And you go to the extreme situation where the string coupling goes to infinity. That corresponds to the situation where, well, there is almost no notion like a geometry. So we have various possible forms of the quantas, and so I have no idea what this is supposed to represent, but that corresponds to the situation where the geometry continues kind of almost always fluctuates, and there is no control over what's happening here. And that, I think the proposal in that case is that each of the so-called space-time form, quantum form, corresponds to this kind of atoms.
I understand that, but suppose I'm taking this thermodynamic limit, or even not, but large, any local fluctuation there, like to map to 2 BPS states.
So you're talking about this division, not about this division.
Somewhere in between. Okay, good.
Yeah, so probably you can continue the discussion afterwards.
Any more questions?
Sorry, I have a basic misunderstanding. So you're talking about Calabi-Yaus, but in some sense you keep talking back about C3. So
sorry. So this is just an example of C3.
Right. So is C3 is?
Yeah, C3.
So you are trying to ask the question, how would that quantum C3 look like?
Right. Well, that's a very special case of our general proposal. So our proposal applies to all Toric Calabi-Yau manifolds, but C3 is just a single, very special example. And I was explaining this in the case of C3.
But all your Calabi-Yaus are non-compact, right?
Right, non-compact.
And so this type of quantization of Calabi-Yaus, is that in the context of what strings here? Topological strings here?
Well, the housing problem, physical type 2A strings here on Calabi-Yau manifold.
Type 2A.
Yeah, type 2A string theory on Calabi-Yau manifold is various DP branes up in P cycles.
So you're saying that there is an understanding how to quantize any Toric Calabi-Yau. What is kind of the crystal melting picture for any Toric Calabi-Yau?
Right.
Any non-compact.
Any non-compact Toric manifold.
Okay.
Yeah. So probably the natural derivation is to go beyond the Toric condition. But if I don't have a torus action, there is the practical. Of course, I can think about such objects as a moduli space or supersymmetric quantum mechanics, but there exists no localization, for example. So the practical computation is difficult. And of course, another question is to consider the case of compact Calabi-Yau. But then again, of course, the gravity does not decouple, and of course, there is a certain discussion about, say, wall crossing phenomena in the case of compact Calabi-Yau manifolds. But that's again another story.
But for example, if we look at type 2 strings here, right, and the Calabi-Yau conditions are being modified if we, go beyond say supergravity approximation.
I see.
So which sense does it? So in some sense, I want to know. So are you talking about alpha prime?
I see. So probably you're worrying about whether the alpha prime corrections might change the results, for example. But the point is that I'm considering BPS states, or in other words, beta index of supersymmetric Quiver quantum mechanics. So that is protected by various quantum corrections.
So you are exacting G string, is that the idea? But
Right.
sort of
Since
really more than alpha prime. Is that
Well, even if we include alpha prime, I don't think the result changes.
not in the case of BPS. Well, I mean, this is not quite clear to me. I mean, if we so are you saying that you're doing a quantization of Calabi-Yaus in which you restrict yourself only to BPS? I mean, I thought your message is that the BPS states quantize a Calabi-Yau, but
Right.
that's probably not full story, right?
Because you are talking about non-BPS vectors, or?
No, we know that Calabi-Yau manifolds, I mean, the condition of Ricci flatness is modified by alpha prime corrections in, in supersymmetric background. And so I'm asking you, what are you quantizing in, say, real type 2 string? If I take real type 2 string theory, what regime you are? So you're telling me that, oh, everything is protected, but I'm saying that the Calabi-Yau condition is modified. So I'm asking you what kind of Calabi-Yaus are you describing by melting crystals? Exactly in which regime?
You mean alpha prime or GS?
I'm asking you, I don't know.
Oh, okay. So if you're talking about GS, for example, and then basically I'm talking about the region where GS is order boundaries. So if you're taking the region where GS goes to 0, you are taking some dynamic. That's also I was discussing that basically the order where GS is order 1. And if I consider the region GS goes to infinity, that corresponds to quantum forms and so on, which I don't understand. That's the answer for GS. And for alpha prime corrections, since I'm so one of the possible caveats is that I'm considering symptomatic gauge theory, for example. That's just a lower description. So the question is whether the alpha prime collection might change the results, for example. But about that point, I'm computing the index, which is protected. So in a sense, we are doing this kind of semi-classical currently.
So I guess maybe you set an aspect of Calabi-Yau geometry are protected, but some other aspects like metric.
Yeah, metric should also be. For example, metric should also completely different. In this case, for example, if I believe in what Kuman says, for example, we are considering the blow up of the geometry, for example, and of course the metric changes if I blow up the geometry. And so, I don't think the metric is preserved.